Okay, so hi all. In this video we will, this one. In this video we will start into, or finish really, actually, our last couple of rules here in the chart. So I'll start here, and then we'll get the sort of transform piece off the ground with these last two characters, and then next week we'll take the week really to just revisit spring problems, the spring vibrational problems, using these and other now sort of newfound functions, and see if it agrees with our intuition about what the spring's supposed to be doing, and so on and so forth. Well, we'll get to that next week. But but to wrap up this week, the last thing that's in the chart. So here's a look at our chart, and I think we've got we certainly have experience now using 1 through 5. Those are sort of our building block or our basic functions. The videos this week were mostly about getting happy and familiar with 6 and 7, or 6, 7, and 8. But who else is in here? So if we scroll down to the end of the chart, of course we already were doing 12, 13, 14. Those are just our transforms of our ODE, right? Y and Y prime and Y double prime. But the three in the middle here, 9, 10, 11, are the ones that probably, if you looked at this chart on the first day a couple of weeks ago, most of these characters were familiar. I think all of the other ones should have been like, oh yeah, I know what cosine is, and but these three in the middle here, 9, 10, 11, these are different, right? I mean, I see a thing called UC. I don't know what that means. Apparently, there's a rule for just that, or if it has something else. And then there's this thing. I don't even know what that is. So these three, these two characters anyway, this UC, and then 11 is what's known as the delta function, are the ones we're going to learn about today. So we'll know not only what are those functions, but also have some idea, at least, of their transforms, which of course are here in the chart. So just like all the other characters, the transforms are actually just right here. So for the three we're going to talk about today, 9, 10, 11, the transforms are over here. While I'm still looking at the chart, and before we go into notes, let me just at least point out, looking at these three transforms, they are actually, you might argue, the simplest. Yeah, I don't know about that, but maybe the simplest. But one thing that you're really asleep at the wheel if you're not noticing is that these three have E in them. The transform they all have. In fact, they're all just sort of slight variations of E, with some other stuff, and they're the only ones that have E in them. So if you look at the transforms of everybody else in the chart, nowhere do I have an E. So these are easily recognizable. So of course, the name of the game that we're playing, that we'll still be playing, even with these guys, is I want to use these to solve ODEs, and the way I'm going to use these to solve ODEs is, or the way I'm using transform to solve ODEs is to take the transform, I get a whole mess of stuff, and then I have the sometimes daunting task of taking my transformed stuff and having to back it up and move in reverse to be able to get the inverse transform of whatever it is I'm looking at. And that can sometimes be a challenge to figure out strategically, how do I know which rule I should be shooting for? And even though I've tried to give you some good advice about that, there's still a certain amount of practice makes perfect and trial and error and whatnot. So, but one thing to tuck away is that for sure if you see E, these are the only ones that have E. So if you see an E and you're trying to do the inverse transform, you're going to have to either be using 9, 10, or 11. And telling the difference between 9, 10, 11 is going to be pretty easy. This one is just the E. This one's got the E and then divided by S. And then this 10 is going to be all other cases, because big F of S could just be anything. All right, so I haven't told you anything about any of these things yet, but since we have the chart in front of us, I just wanted to point out some notable things about these three rules that we're going to dive into right now. Okay, so let's do the impulse function first. this is rule number 11, so we'll do 11 and then we'll do 9 and 10. The U is a little trickier. But the impulse function, so what is this first of all? So what that weird character that we saw. So we define the impulse function, that's called the unit impulse function. The notation for that is, so this is a lowercase Greek letter, delta. Is that sort of, I don't know, scripty kind of letter. So delta of t is the notation, or the usual symbol that we use for this impulse function. And it's this lowercase delta of t. So we define the unit impulse function, delta of t, to be a function which is defined to be 0 everywhere. Well, that would be that would be an interesting definition if I stopped there. But is defined to be 0 everywhere except near 0. And what's true near 0, where it has, we might just say, a very large, I'm going to be a little cute here, value. Okay, we'll call that a sentence there. Okay, so, right. So I'll read this to you. So this delta of t function is a new character for us. And what does this mean, and what's the definition here? So, so this impulse function is a function that's basically always 0. So in other words, it's not doing anything. It's just 0. However, near t equals 0, it takes on very large value. Obviously, I could try to say something like infinity, which is a little misleading. So I'm going to draw you a picture, which is going to hopefully clear this up. So, but that's the idea. Why is it called an impulse function? Is because if I say the word impulse to you in English, aside from meaning something that candy bar that you buy on your way out of the grocery store, from a physics perspective, impulse, I think usually sort of means a quick hit, right, or some force. But if it's an impulsive force, it usually means it's very brief, as opposed to a prolonged force like a wind blowing. That's not an impulse. But something very quick like a punch is an impulse force. So that's what it means here too, right? So the idea is that an impulse function is a function that's basically 0, right? It's not doing anything. But right near time 0, it actually does have a large but brief value. So let me draw you this picture. So usually we imagine, if this is a graph where that's time, and that's, delta of t, right? Okay, the function I'm graphing here. Then how do I define this function? So let's go in a different color here. So the delta function is defined to be 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, but right near time 0, which obviously is the y-axis here, it has a very large value. So I'm going to do my best here to... There, that's pretty good. All right. So I'm not going to, get overly dramatic or fancy about any of this, but I will say I'll give you one little note about who this is or how you come up with this. But this is the idea, right? So it's almost like a heartbeat kind of thing, where it's nothing, 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 and then you get a quick blip, I guess they would say, right? And then it's back to nothing. So as it is, right, the classic delta function is this impulse. So that's what this is, right? This is an impulse. As it is, it occurs at 0, at time 0. Now, as we're going to do in a minute, we're going to sort of move this over a little bit. But I'll give you just one last little bit of trivia, I guess, or some information about the impulse function. So, I can't really say exactly, or I'm not going to write down a formal, well, so what's the value here, right? If that's a dot, what's the value? Well, let's just not maybe think about that too much. Let's instead think about it's a very short, right? This is doing nothing, 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 and then there's a big punch, and then it goes immediately back to doing nothing, 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 nothing. That's the best way to think about it, right? So just so you don't think this is total BS, I will at least say, what about, what more could we say about this? So if you integrate the delta function, obviously, I'll say negative infinity to infinity, but obviously, since the function is basically 0 everywhere, you're not getting much. But of course, we would all say, hopefully, that the integral of this would be the area under the curve, which I think would be, here, let me actually do this in a different color here. I'll go green here. Right, so of course, let me see if I can shade this in without wrecking my picture. Right, so that little guy in there, that would be the green, right? If I do the integral, it would be that area, the area under the blue. That has to be 1. So just to give you some sense that this isn't like a magical thing or like an infinity thing, this is grounded, right? This is grounded in the idea that the integral of this is actually just 1, which in some sense is saying, why is it called the unit impulse function? It's because the integral is 1. So you're delivering a 1 unit amount of force. The idea would be instantaneously at time 0. So I'll write that down just for the physics people in the room who want to know, so wait, so what is this? So the idea, right, so I'll just put this in quotes so you can see I'm talking about human world here, right? So the idea is that delta t delivers a force of size, or strength if you want, 1 at time 0, okay? Now you might say, oh, well, what does the graph have to look like in order to have the integral be 1? Okay, let's not get too carried away. We can all sort of see, oh, yeah, okay. You could probably pull that up high enough. Of course, it depends on what's that value and what's that value. Okay, this is where I think we are hopefully all happy to not go into super crazy calculus, rigorous math details, right? But that's the idea of what an impulse function does, is if we're going super, just a human understanding of this is a quick punch at time 0 that's delivered, and then that's it. So if you think about a punch, that's what it does, right? You punch something or punch somebody. You wouldn't say that there's any sort of prolonged force. It is an instantaneous force. It's delivered and then it's over. That's what this does. Okay? So, all right, so since as I already said, we're going to return to spring problems, or we're obviously sort of talking more about a physics kind of a thing here. Let's say that I have an experiment. We're going to come back to the spring, right? But whatever kind of experiment I have, and I want to use one of these impulse functions. Well, while you might say you want to deliver an impulse at time 0, sometimes you might say, well, I would rather deliver the impulse at time 5 or something like that. So so you may use delta exactly as is, but let me go back to my red here. But we may also just shift it over a little bit. So while delta of t by itself delivers a force of size 1 at time 0, we more commonly use. Sorry, I should not try to squeeze this in. Let me just go to another slide here. So instead of using it as is, we more commonly delta of t, and we probably shift it by c. So of course, what is this? This is same. I'm just going to give this to you in English, right? This is an impulse of force 1 at time c. Okay? So we started talking about this whole shifting thing. So now anytime you see t minus c, c is a number, right? But anytime we see something like this, I don't want you to be like, oh my gosh, what the heck is that, right? It's just the original whatever this is that we're looking at. In this case, it's this impulse, this punch. But when you do a t minus c, that just means you're shifting it to do its job at time c rather than at time 0. So if I did this, right, I'll give you the graph of this too, which should hopefully then make a little more sense as to why this is actually more of what we're going to use. So who is this, right, or what is this doing for us? So this is going to end up being, right, 0. I don't remember what colors I was using, blue. So this guy here is going to be 0 up until time c, and then it's going to do its impulse. And then go right back to 0. Okay? So that's f of t minus c, right? That's this character. Okay? So more commonly, if we think about an experiment that we might be doing, again, we're going to go back to the spring. What if I want to say, at time 6, you fling, maybe I wouldn't say punch, but you flick or you fling the spring. You give it a whack. So, spoiler alert, we can use an impulse function in order to say, oh, if I do the impulse function at c, what if I do c equals 6? Then that's equivalent to me saying that you want to give this a flick, right, or a fling at time 6. All right, so an impulse function, we're obviously, you can probably talk about this forever, but just in our limited examples, that's what this represents, right? So the impulse function just represents the ability to deliver a force at any time you want now. So if you shift it over to time c, that's what that will represent. Okay, so of course this is the one. This is the one you actually see in the chart, right? So according to the chart, the Laplace of the impulse function at c is just quite simply e to the negative cs. And that's, what is that, rule number 11 I have here in my notes. Okay, so if we have an impulse function, you know the transform now. I'm not going to do a proof of this. It actually gets a little bit yucky, just because, well, anyway. But maybe it kind of makes sense, right? That since the transform essentially just uses this anyway, right? The function we're transforming by is e to the negative st, and since this is basically 0 everywhere, hopefully it kind of makes sense that the only place it exists is at c. So, well, anyway, okay. So if we have an impulse function, which we will next week when we look at our spring problems, the good news is the transform is easy. It's right here, and all right, and we'll see what we're going to end up doing with that. So I'm not going to do much with this right now. I mean, I could do an example for you, but this is pretty lame. Right, this is it. All right, so impulse function, great. So that's one type of character. Now I will say, since this is going to make an appearance in ODEs, you don't know, I think every single Laplace transform problem we've done in these last week and a half, you've known how to solve. But if I put an impulse function in an ODE, you don't know how to solve that, right? We have no way of actually doing that. You can't use stuff from the last exam or from anywhere in the course because we never, we have no idea what I'm supposed to do about that. Well, we do, because in the sense that we do know the transform. So if we're doing our newfound transform methods for doing this, we will be able to solve this. So this will be the first of a few problems that finally I can definitively say we would never know how to do this except for with Laplace transforms. So this at least gives us some justification in doing this. So that's one character. The other character that we are going to, so that was the impulse function. Another character that we'll talk about is is known as a step function. That's this u that you see in the chart in rules 9 and 10. All right, so again, let me give you a definition. So we define the unit step function, and the notation, the unit step function at C, and the notation for that is u subscript c of t. To be simply this, I'll give this to you two ways. I'll give it to you the algebraic way. So I don't know that we've done a whole lot of, I think in algebra or pre-calc, we called these piecewise functions. These are these functions where you describe, you say, here I'm making you a function, and sometimes it behaves a certain way and sometimes it behaves a different way. So this is one of the easiest examples you'll ever see. So it's 0 if t is less than c, and it's 1 if t is greater than or equal to c. So it's a very simple idea or concept here. All right, I'll give it to you. I'll give you the graph as well, in case this isn't clear what this does already. So here's time, and here's c, and here's 1. So if I graph, in blue here, if I graph uc of t, then it's simply, so what does this lingo or notation mean? It just means that this is equal to 0 when t is less than c, and it's equal to 1 when t is greater than or equal to c. So if I was drawing you a graph of this, I think I would say, so it's 0 up until c. If you really want to be fancy, I think back in whatever class, we put a little open dot there. And at c, it hops up here to 1. And you can put a solid dot there if you want, since the or equals to is included there. And then it's 1 forever. Okay, so it's obviously very clear why it's called a step function, because of course, you know, if you imaginarily drew that vertical line in, it would look like a step, right? Technically, that line's not there though, so we'll. This is a discontinuous function. So, but it's simply this, right? So it's simply 0 up to time c, and 1 after time c. Now, okay, so that's the thing, I guess. So let's again think real life. What is this used for? What does this mean? So the impulse function that we just talked about means, right, that at time c, I'm giving it a quick flick, right, or I'm a quick punch. But as soon as I go up, I go right back down. Well, that's not true for a step function. So this is not saying that at time c, you give it a quick punch. In fact, if I was thinking about this in human world, this is saying you do nothing up until time c, but then after time c, you give it a force. If we're using this to represent some sort of a force, you give it a force of 1 forever. Now, that's not a punch. That's a lean. That's a, I'm not going to punch somebody who's standing next to me. I'm going to, with my shoulder, probably just lean on that person forever, I guess, right? So I'm imparting a force on them forever, though, not just for a quick hit, right? So as is, sure, this might be a thing, right? So thinking again about spring problems, the idea is that I might say, well, maybe I run my spring and I let it bounce without any sort of, or let it do its thing, and then maybe at time 6, just to make up a number there, I introduce a fan that I turn on at time 6. A fan would be a good sort of human example of something that delivers continuous, steady, constant force like this. So maybe somebody, the experiment calls for turning a fan on or some, analogous version of that at some given time. So you might use the step function as is in order to say something like that. But most of the time, we use the step function to represent an on-off switch. So I'll say most of the time, notice we have any function, just some random function f of t, notice if we have any function f of t, if we, sorry, I'm struggling with grammar here, if we do uc of t times f of t, then what is this going to be? Sorry, I didn't leave myself enough space here. Well, what does uc, right? So uc up to times c is 0. So this is going to be 0, and I don't care what f of t is. 0 is going to kill whatever f of t was. So this is simply going to be 0 if t is less than c. Now after times c, this is uc is just 1. Okay, that's fine. So then this is just f of t. Okay, so in some sense, what we usually imagine in this case, or if we did something like this, right, we'd be saying, or we'd be thinking about that uc of t is like an on-off switch. Right, it's off, or it turns this whole thing off up to time c, and turns it on after time c. Which is like this too, right? I mean, this is just happens to be 0 and then 1, but you don't have to be married to it being 0 and 1. You could say it's 0 and whatever, right? Whatever you want. So a step function in practice, most of the time, if you ask someone, what is this used for? A step function is used to basically be a light switch, right? Or some sort of switch to say, start with it off, and then at some time, turn it on. So maybe rather than me leaning into something at time c, I activate some whatever, right, other force that maybe is not necessarily constant, but I flip the switch on at time c. Okay, so most of the time we're using uc in conjunction with another function is what I'm trying to say. Okay? Now, before we get to the Laplace of this, to keep going with this, I got to go to a new slide here. Right, so of course, so for a function f of t, I'm just going to make up a graph here. Right, so if I have some function f of t, I'll just make anything up here. Whatever. So if that's f of t, then if I do a step function times f of t, then wherever c is, I don't know where c is, I'll just make it up and say it's here. What does that do? Well, that turns it off completely, so I get 0 up to c. Oops. And then at c, I don't know where c is in my picture over here, I'll pretend it's sort of there. At c, I turn it on. I'm going to do my best to copy what I had over there. Not the best, but okay, whatever, okay. Right, so the difference between red and blue here, right? So if on the left here in red, I just have I just made up this function, just some squiggles here. Then if I do uc times f of t, I would simply lop off, wherever c is, if it's right there, for example. I lop off this, and I replace it with 0. And then I say, oh, okay, now after c, pick up the graph and do the same thing. Sorry, even though my picture is driving me crazy. Doesn't quite look the same. There, that's maybe a little bit better. Not much better, but well, anyway. Right. So that's what this says. So now, The reason why this is less than ideal is, again, our old friend, the shift, is going to make an appearance here. Is that, this nice function f of t in red over here, it had its big day. It was finally going to make it out. It was going to be part of this problem. It was, you're going to do something with the spring with this or whatever, maker space something or other. You're going to make something. You had all this nice stuff here. You were ready to go. And look what you've done. You've massacred it, right? You chopped off this whole front piece. Now, there was quite possibly some valuable information or, there was some behavior there that you might have wanted. So what I'm trying to tell you with a cute story is that typically in designing things, we don't typically design something to design this f of t over here to go from, to have all of this information and then chop some of it off just because we don't want it to turn on until time c. It's much more typical that rather than doing what I did in blue here, sorry, let me color coordination in effort a little better here. Rather than doing blue, I more so want to do green. I more so want to say, you know what? Don't chop it off at time c and lose this whole front portion. Instead, what I'd actually like to do is say, if I have a need for a step function, right, which again is like a light switch or a switch that you turn on and off, and I do want to do that action at c, it's more likely that what I want to do, rather than chopping off the front of the graph and just copying the rest over, is that I actually just wanted to pick the graph up and move it over. So more so what I probably want is this. If I have a need, because of timing of my experiment, I want it to be off up until c, but then I actually want all of f of t That's more so what I want. Or most applications would say, if you want a delayed start or something like that, right? I want you to, instead of starting it at time 0, start it at time c. Most of the time, this is what you want, green. Not so much blue. But what's green? Well, green, if you think about it, how do I, right? So I'll say most of the, let me write in some words here. Most of the time, sorry, I didn't mean to put a comma there. Most of the time we use a step, which is like a light switch. We want to shift the graph, not lop it off like in blue. All right? And in particular, what's actually nice about this is that, especially because this one starts at the origin, is that green down here is now what we might call continuous. In other words, I've pasted it together so that it actually does flow, right? I'm 0, 0, 0, 0, 0, and then at C, I start doing my whatever, this thing, this wiggle. Right? So green is the way we want to go. But what's green? Well, I still have a step function here, because of course that's what tells me B0 up to time c. But if I just do f of t, that means I'm simply going to turn it on wherever it happened to have been at time c. But I want it to turn on at time c, but be the value at time 0. So for that, I need to shift by c. Right? So this whole shift, which is the word of the day, I guess, right? T minus c. T minus c means do exactly what f of t is, but move it over, move it to the right, c units. So, or you could say from a experimental process, delay it starting for c seconds or minutes or whatever. Okay, so most of the time, when we're doing an experiment using a step function, this is what we're going to use. And for that is the reason why in the chart you see rule number 10, which tells you exactly how to do what's in green here. Okay? So let's pull this together now. All right? So either we have a step function just all natural, or probably we want to do that step and shift thing. So let me list these for you. I'll actually do a derivation of the first one because it's easy. All right, so we'll do two transforms. So the chart has the transforms of both of these characters, just the step function by itself and the step function in conjunction with a shifted function, little f. All right, so you see these are rules 9 and 10 in the chart. All right, since this one's easy to do, so I'm going to do it. So the Laplace of t minus of uc, sorry. So just by definition, so we don't lose track of that these actually do have definitions from calculus. Remember, our definition of a transform is you integrate from 0 to infinity, negative st times the function, which in this case is uc. Okay, well, uc is our best friend when it comes to doing integrals, or anything really, because of course uc is simply 0 or 1, which means it's either going to annihilate everything, or it's going to essentially be invisible, right? 1, when it's 1, it might as well not be there. So hopefully you agree that how would I evaluate this? Is I might say, well, uc is actually 0 or 1, so if I'm between 0 and c, I'd have e to the negative st times 0, which we can all tell how much that's going to be. And then from c to infinity, uc is simply 1. Okay, so anytime you have a piecewise function and you're trying to do math with it, you pretty much just want to break it into the two pieces, so it's 0 or 1. Well, this is, of course, 0, because you're integrating 0. And over here, well, I could do that integral. That's an easy one, right? I just have e to the negative st. Remember, t is the variable. S is just a constant. So I'd end up with 1 over s e to the negative st. And now I'll have bounds to plug in. C to infinity. Okay, so let's see. I'll just keep going here. So when I plug in infinity, what happens here? So just like with all of our problems, we're generally assuming that s is positive, right? That's how we're defining all of these transforms. So since s is positive, I'll write that in parentheses over here. Since s is positive, when I do t equals infinity, I have positive s times infinity, so this is positive, but then there's a negative in front of it, so it's negative. And we all know that e to a negative big power is going to be 0. So when I do the infinity, I think I get 0. Now when I do the c, what do I get? So first of all, I'm doing top minus bottom. So I have minus negative 1 over s e to the negative sc. Okay, also known as e to the negative sc over s. And that's exactly what you see in the chart. Right? So the Laplace of the unit step function is that. And again, right, that works only for positive s's. And that's rule number 9, I think, in the chart. Okay, so we just did a little proof of that. Just stay honest here. Okay, so that takes care of that one. The other one you can show if you're kind of feeling adventurous, but I'm just going to write down the second one. the rule, which is rule number 10. And then we'll do a couple of quick examples using 10, since that's the one that we're going to use quite frequently, actually. Okay, so that's rule number 9 shown to us. And then, of course, from the chart, number 10 says if you want to do the Laplace of a step function times a shifted little f, then you can, and you just get e to the negative cs times big F of s, where, and here's where I have to be very fussy, I guess, or something, where big F of s is, of course, the transform of little f of t. Now, underline, exclamation point, careful. Okay. So here's where everybody gets this wrong, or if you get it wrong, it's because you forgot one small but important thing. Okay. So let me read the rule to you, then I'll make sense of my crazy histrionics over here. So, so the Laplace of, if you have a step function times a shifted little f, is just this. So it's very simple, right? I get the e piece, that's fine. Obviously I can extract the c, I know how much that is. And then big F of s, well, we've been doing that all along. Big F of s is the transform of little f of t. But let me point out, or let me note my big caution, all of that, with a note down here. Big F of s is not the transform of little f of t minus c. Okay? So don't do, some of you are going to do this, don't just be like, okay, cool, so I have uc times something. So the transform is e to the negative cs, that's what the u sort of turns into, and then the whatever's here, I do the transform of this, and I get this. No, don't do that. Big F is the transform of little f of t, not little f of t minus c. Now this is an easy fix, but it's, right, but you got to remember to do it, all right? All right, so no, right, so no, there's nothing, instead, you have to first write down little f of t. So, in other words, from little f of t minus c, you can write down little f of t. Then big F of s is the transform of little f of t. Okay? So, I just make a big fuss of this just to kind of, sorry, remember those. Right, you got to remember to do the one important step, which is the shift, or the unshift, depending on the way you look at it. Let me do an example, since it'll make more sense when you see this in action. I think I can squeeze this in down here. So let's say I want to do the transform of u3 times t squared. Okay, sorry, that's an L there. Okay, so this certainly looks like rule number 10, doesn't it? Right? I have a step function. I have a step function. Of course, c is 3. That's an easy thing to extract. Great, great. And, okay, so that must mean this matches this. Yes, it does. But again, the wrong thing to do is say, oh, okay, cool. So my answer is e to the negative 3s, and then the transform of t squared, when you look it up in the chart, is 2 over s cubed. Okay, so don't be this person, because that's wrong. So what's right then, I guess, right? So erase that. So just be methodical, right? So when I'm doing matching, of course that matches that, yes. Which of course means, so I'm not ready to write an answer down yet, I'm going to sort of say, oh, well that has to match that. Oh, which means little f of t minus 3, because that's c, that has to be t squared. So I encourage you to, before you even start to write down an answer, do a little side problem here, where I say, okay, well, so whatever's here is this. Write that down. Because now I know for my answer, so yes, of course, my answer is coming. And my answer is probably going to be e to the negative 3s times big F of s, right? That's going to be my answer. So I didn't mean to pre-scold you. That's okay to write down. But now you look at yourself and you say, self, what is big F of s? And you say to yourself, hopefully, I don't know. And then hopefully you also say to yourself, how the heck am I supposed to get big F of s? Well, I bet you if you knew little f of t, big F of s is just the transform of that. And then you say to yourself, well, how do I know how much little f of t is? And that's where you just need to think for a second and say, well, that's not little f of t, that's little f of t minus 3. I'll say it fast like that, t minus 3. So if I don't, which I don't particularly, I'm not that excited about that, I don't really care about that, but I do want to know little f of t. So we will do the simple trick of shifting. And I don't know how you want to say this, but usually I like to say something like plug in t plus 3 for t. I know that always looks a little funny, but I'm going to plug in, right? So maybe instead of saying shift here, I'll say plug in this case, t plus 3. Now, if I plugged it in on one side, I better plug it in on the other. All right, so all I'm doing here is I'm plugging in t plus 3 for t. Now on the left here, of course, this now actually is little f of t, right? T plus 3 minus 3 is t. And what do I have on the right? T squared plus 6t plus 9. Oh, that makes a big difference, doesn't it? So little f of t, which I'm still not done yet, but little f of t is actually that. T squared plus 6t plus 9. It's not t squared. But now the answer is in front of me. Because now I can say, oh, well, if this is little f down here, big F of s is little f of t. Big F of s is simply the transform of this. So if that's little f of t, I'm finally ready for big F of s just directly from the chart. So t squared turns into 2 over s cubed. Remember, coefficients come along. So 6 comes along. T turns into 1 over s squared. And 9 turns into 1 over, 9 times 1. 1 turns into 1 over s. So 9 over s. So my answer up here, sorry, I've gotten a little crooked on this, is e to the negative 3s times this stuff. Okay? So just do the little side problem here. This will work every time. So you don't have to, it's just a question of remembering that you have to do it more than, oh my gosh, this is hard. I mean, it isn't, right? Just plug in what you need. And of course, it's just t. If this is t minus c, you're plugging in t plus c every single time. All right, so not hard. Okay, so that's the forward. I'll give you one backwards, and then we'll call it quits here. So let's find the inverse, because of course that's more the direction that we have trouble with. Transform of. I'll give you one as it may occur in a problem. Squared. Yep. Okay, so maybe in the context of solving an ODE, we have this. As we know that this is the last step of solving an ODE, is you have all this S garbage, and you have to somehow magically turn them into inverses so you can write down the solution. So let's say that this is what we happen to have. I need to do the inverse of this. So this is where I'm scouring the chart and I'm trying to figure out if I have something in the chart that matches this, whatever I've got. So as I look through the chart, just like we've always been saying, then look at the denominator. which in this case is s squared, by itself, right? No, nothing else down there. And hopefully your eyes are attracted to the fact that s squared, right, would be the, 1 over s squared would be the transform of t. But of course, I have two terms up top here, and in particular, one of them has an e in it. So in order to make our lives easier, how about I first do the traditional split up, right? This is almost always a let's split this into 2 fractions situation. So let me do that first, right? And then I have this other piece over here, right? E to the negative 2s, and that's times 1 over s squared, or however you want to write that, right? You could write this as 1 fraction if you want. But I'm sort of going for a moment here, so I'll write it that way. Okay, now I'm trying to do the inverse. Now, of course, tucked away in the corner, and by corner I mean the chart, I know that the Laplace of t is 1 over s squared, right? That's rule number 3, I think, right? Okay, so of course to go backwards, I'm just, right, if I have 1 over s squared, that goes backwards to just t. Oh, so if I'm trying to go backwards, I'm already done with that one. Rule number 3 would say that turns into t. Great. But now what the heck am I supposed to do with this? Aha. Well, when I look at the chart and I say, oh gosh, what rule could this be? I don't have a whole lot of options. Right? So rule number 3 is that one, which I already used very nicely. But one that we just learned about today, rule number 10, right, says the Laplace of uc f of t minus c is e to the negative sc big F of s. Right? That's this one that we just learned about. Well, let's see. Well, that's pretty good. And so as long as I say those two guys are the same, I think I could maybe use number 10 to go in reverse. But now again, here's what I say, will maybe emphasize to you. Just be a little bit careful here. So as I'm trying to go backwards and I'm doing my matching, what might I start out by saying? Well, for sure, this is telling me this matches perfectly. And in particular, this is telling me c equals 2. So from the E piece, I can at least extract what c is. And okay, but also to make the matching work, I better insist that big F of s better be 1 over s squared. Right? That's the only way I'm going to have this match this over here. Okay, now you might say, well, gee, why is he being so slow about this? Well, just to be careful here, right? So when I go backwards, in some sense, right, it's fine to say E turns into the U, and big F turns into this. So in other words, in order to write down my answer with rule number 10, I have a minus sign up here. This is going to turn into U2, right, U2, because C is 2. But in order for me to fill in what goes right here, just again, be careful. In the chart, I need little f of t minus 2, not little f of t. Now, fortunately, this direction's easier. If big F is 1 over s, then little f of t is t. That's rule number 3. Right? 1 over s turns into just t when you go backwards. And so what should I fill in down here? So since I know that, little f of t minus 2, because that's what I need, is of course just t minus 2. Right? So down here, I'm going to fill in, get rid of my underline here, t minus 2. And that's the answer. Okay, so it's just these little shifty, both I mean that literally and kind of figuratively, these little shifty things that you have to do. Just don't forget, right? None of them are hard. You just have to sort of remember that they're there. All right, so this is the inverse transform would be those guys. Okay, so that's all just sort of, I don't know, nonsense, I guess, or just algebra and calculus and transformy stuff, which is all not very exciting by any means, of course. So we do need to see a little bit about, so how will these come up, right, or where will we use these? So like I said, for that next week, we will revisit spring problems, and we'll use these. We'll use the step function, we'll use the impulse function, and we'll see some really neat things, actually, some really neat solutions emerging, and we'll do some really nice analyses of those. So good luck with this. There's no homework problems on impulse and step. Those will be for next week. So the ones that you're working on for Friday of this week are all before this, right? So hopefully you've had a chance to start those and made some good progress through those. But those are due Friday this week. So please make sure you check those out. And I will talk to you on Monday.